Hello everybody. In this video we'll be covering one of the sections in chapter 4 of our textbook entitled Atoms and Elements. Hello everybody. So in this video we're going to dive into the periodic table. So it all started with this guy, a Russian chemist by the name of Mendeleev. And other than just having fantastic beard game, he's very interested in the elements. He wants to find them all, and he wants to kind of categorize them. So he starts to order the elements in a table according to their atomic mass, because we can now weigh, we have different ways of weighing these elements at this point. And what he saw is he started to see a repeating pattern of the properties. He'd see that, this element's like this, it's like this, it's like this, it's like this, it's like this. And then all of a sudden he starts to see one that looks a lot like the first one. And then it repeats over and over again. So he comes up with what he calls his periodic law. So he says that when the elements are arranged in order of increasing relative mass, certain sets of properties recur periodically. And that's where it comes up with the periodic table. And he's able to use this pattern to predict the properties of even undiscovered elements. So he's starting to be able to predict that, I think that there's one that we're missing here, and I think it's going to have properties that are going to look like this. And where the atomic mass orders didn't fit, he started to order them according to the other properties. And really this was an indication that it's not really appropriate to order them according to their atomic mass, that there's something else going on there. And so this is what his table looked like. And you can see that he was actually able to recreate pretty accurately the first set of main group elements, right? He's got the order right. He's pairing them right. It's only when you start to get into the heavier elements and stuff that his system tends to start to break down. So let's go over what we now know about elements, and then look at the modern table and see exactly how we've gone about doing this now. So what we now know is that each element has a unique number of protons in its nucleus. Okay, for instance, all carbon atoms have 6 protons in their nucleus. The number of protons in the nucleus of an atom is called its atomic number. Okay, so remember that the atomic number is synonymous with the number of protons that are in an element. The number of protons in an element dictates which element you have. Okay. Sometimes the atomic number is abbreviated with a capital Z. And so, again, because each element has a certain number of protons, it is identified by its atomic number. And so what we're doing is we're going to start to arrange the periodic table in order of the atomic numbers and not the atomic masses. All right. And we've given each element its own unique name and symbol. These symbols are either 1 or 2 letters. The first one's always capitalized. The second one's always lowercase if there is a second one. Some of them make sense and some of them really don't, because they're using like these really old words for them and stuff. A lot of this was actually laid out in German originally, so it tends to be a little weird. But this is an image of our modern periodic table. And you can see, for instance, over here, right, with the tellurium and the iodine that we mentioned before, iodine is actually lighter than tellurium, but it has an extra proton, so it should actually go after tellurium. And you can see that that's also true over here with the case of cobalt and nickel. Cobalt's heavier than nickel, but nickel has more protons, so it should actually go after it. So that's where Mendeleev's systems kind of broke down. It didn't really predict things just the correct way, because he really didn't have a way of measuring the number of protons yet inside of the elements. If we zoom in on one of these guys, we can see how this is all laid out here. So we're going to have this top number here. This is the atomic number. Again, that's the number of protons in a potassium element. We have the atomic mass, and that's going to be in AMU, right? So that's going to be the mass that the atom has, and that's going to come from its protons and its neutrons. And then we have the element symbol, right? And again, sometimes they make sense, sometimes they don't. This one's a capital K. We won't really associate that with potassium, but I'm sure there's some old word that actually they used to use in place of potassium. I do know a few of them, like iron here. It stands for ferric, which is like Latin for iron. Tungsten is capital W for wolfram, which I believe is German word for tungsten that they used to use. And then they even get kind of silly as we move down the periodic table to ones that have been discovered more recently. This one is not complete. I mean, there's Rutherfordium, there's Einsteinium in there, so it gets to be a little weird down there. Okay, so let's do a couple of questions. These are the types of questions that I'm going to ask, and you're going to have to use your periodic table in order to answer them. So let's start off with, what is the atomic number of boron, which is a capital B? Grab your periodic table and take a look and see if you can answer that. What is the atomic mass of silicon, Si? How many protons does a chlorine atom have? Remember that the number of protons is going to be the same as its atomic number, right? How many electrons does a neutral neon atom have? Remember that if it's neutral, that means that it has the same number of electrons as it does protons, and that the number of protons is going to be the atomic number. Will an atom with 6 protons, 6 neutrons, and 6 electrons be electrically neutral? Will an atom with 27 protons, 32 neutrons, and 27 electrons be electronically neutral? Will a Na, so sodium atom, with 10 electrons be electrically neutral? So the atomic number of boron is 5. The atomic mass of silicon is 28.09 AMU. You may have gotten a slightly different number for that. It depends on which periodic table you're looking at. How many protons does a chlorine atom have? So it has 17 protons. That's its atomic number. How many electrons does a neutral neon atom have? It's got 10, because it's got an atomic number of 10. Will an atom with 6 protons, 6 neutrons, and 6 electrons be electrically neutral? Yes, it will. That is a carbon atom, and we know it's electrically neutral because it has the same number of protons, which are positively charged, as electrons, which are negatively charged. So 6 positives, 6 negatives add up to be neutral. It doesn't matter how many neutrons we have because they don't have charge. And we find that's true here too. We can change the number of neutrons. We don't have to have the same number of neutrons as we do protons and electrons. We can have as many or as few as we want, and it will not change the charge. The only thing that's going to change the charge of the overall atom is a misbalance between the protons and the electrons. If there's more or fewer electrons than protons, then it's going to start to take on a charge. And we're going to talk a little bit more about that in the next section. Will a sodium atom with 10 electrons be electrically neutral? No. Okay, and we know that because sodium's atomic number is 11, okay? Meaning it has 11 protons. If it has 10 electrons, it's not going to be neutral, okay? Because it does not have the same number, right? So the first thing we're going to do with the periodic table is there's a lot of information packed into it, and we basically just keep breaking it down into smaller and smaller groups and talking about their properties. So the big three, the biggest, the largest groups we can group them into are metals, metalloids, and nonmetals. Okay. You can see that the majority of them are metals, and that they're going to be located on the left-hand side of the periodic table. On the right-hand side, the next largest group are our nonmetals. And then along this little step right here, we have our metalloids. So let's talk about the difference between metals and nonmetals and metalloids. So metals, they're usually always solid at room temperature. One big exception is mercury. Mercury is just kind of weird. They tend to be reflective and shiny. They tend to conduct heat. They conduct electricity. They're malleable, meaning we can shape them specifically to stamp them into a thin sheet. They're ductile, so we can draw them out into wires like we do with copper and aluminum for our houses. They tend to lose electrons and form cations in reactions, and we're going to talk about that in the next section about ions, what exactly that means. But it's important to know that metals tend to lose electrons. They want to give up an electron. And about 75% of the elements are metals, so the majority of them are metals. Nonmetals, they're found in all three states, so they can be gases, liquids, or solids at room temperature. They conduct heat poorly. They conduct electricity poorly. As solids, they tend to be brittle instead of being malleable or ductile. Crucially, they tend to gain electrons in reactions to become anions. So nonmetals want to gain electrons, metals want to give electrons up. And we find them on the upper right hand of the table. An exception to this is hydrogen. Hydrogen is just kind of weird. It is a nonmetal. It is at the top left of the periodic table. And that's because there's some real special properties to hydrogen because it is the smallest atom. It's a little unique in some of its properties. So metalloids, they tend to show some properties of metals and some of nonmetals. They're also known as semiconductors. Mostly they conduct heat and electricity, but only sometimes and only under certain conditions. And this is actually really, really beneficial to us. Silicon, for instance, is a big commodity, pure silicon. This is what's allowing us to make all of the transistors and capacitors and stuff that are inside of all of our electronics. And it is the property that it will sometimes conduct electricity, but sometimes not, that we're actually using to create all of our computers and stuff like that. So these are an important class of compounds or elements. So let's do a little practice here. Let's classify each element as a metal, a nonmetal, or a metalloid. Okay, so get out your periodic table and let's do a little lookup. Let's see if we can find xenon, tungsten, bromine, arsenic, and cerium. Okay, so xenon is on the far right, furthest right down the table, so it's a nonmetal. Tungsten is towards the center, and it's going to be a metal. Bromine is on the column second from the right, so it's a nonmetal. Arsenic is a metalloid. It's along that step thing. And cerium is a metal. So let's talk a little bit more about our modern periodic table, and we're going to continue to break it down into more and more parts and smaller groups, kind of categorize our elements a little further. So elements with similar chemical and physical properties are in the same column, and these columns are called groups or families, and I typically see them called groups, and they're going to be designated by a number, and the numbers are going to go up as we go along, and you'll see that. The rows are called periods, and they also have a number. And each of the periods shows a pattern of properties repeated in the next period. So we're going to see a set of properties in one period, and then we're going to go down and across again, and we're going to see the same pattern of properties repeated. So we have our main group or representative elements, and I'm going to show you in a moment which exactly are called the main group elements, but these guys tend to have properties that are going to be important for us in the next section about ions and stuff, because we know something about these guys. Then we're going to have our transition elements. These are all called, these are all metals, so they're often called the transition metals. And then we have the inner transition elements, or what they sometimes call the rare earth elements. And these are all metals, and they really belong in periods 6 and 7. So let me show you a little bit about what I mean here. So any of these, so this is a group, and then a row here is going to be a period. So any of the groups that go above this line here, so this one, 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 and this one, these are all our main group elements. This block here is our transition metals. And then this block here is our inner transition metals. And the weird thing is that we're really just compressing this table down so it fits on the sheet. This block here actually belongs right here. They just pull it out and then stick it down here. It's just to represent the table. Is for actually, I could actually upload a periodic table where they don't do that, and they just do it in this long format, and you can see that they all actually fit together. So within those groups, our main group elements are transition metals and our inner transition metals. We also even have a few more groups that kind of have a lot of historical context, but it's still useful to learn about. And the first one here is going to be our alkali metals in this first group. The next one is going to be the alkali earth metals, or alkaline earth metals, sometimes you'll see it called. We have our transition metals. We have our noble gases over here. There are the halogens. And then the lanthanide series here. And then this is the actinide series. And most of the guys down here, they're all really heavy atoms. They tend to all be radioactive. I'll also mention that there are names for these other ones too. I'm just not gonna make you guys get into all of that, but they all have their own little names with their own little historical context. So let's talk about a couple of the important ones. Let's start off by talking about hydrogen. So it's a non-metal. It's a colorless diatomic gas. It's in the air. You would never know. It's very prevalent. It has a very low melting point and density. It tends to react with nonmetals to form molecular compounds. So it would react with chlorine to produce hydrochloric acid. It would react with oxygen to produce water. And this is pretty key. It's fulfilling a big function that we need in order to make the type of biological molecules that keep life alive. And it even tends to react with metals to form hydrides. And then it will often react with water, if that's present, to form hydrogen gas. You may know the hydrides from the batteries, like nickel metal hydride batteries and stuff. And you may know that if those pop open or start to leak or something like that, water will get in there. And then it'll start to form this hydrogen gas, and that can be dangerous and make the batteries explode. Hydrogen halides dissolve in water to form acids. So that's what we were talking about here. So we're going to talk about the halides, the halogens, and they tend to form these acids that we're familiar with: hydrochloric acid, hydrobromic acid. So the group 1s are the alkali metals. Hydrogen is usually placed here, but it doesn't have the same properties as the alkali metals. So that's why it's a little confusing. Again, hydrogen's special because it's the smallest one. They're soft, they have low melting points, and they have a low density. You can usually identify them in a flame test from one another. This is one of the ways that they first were identifying them. So they would have all of these metals that looked kind of similar to each other. They were all soft. They're all melting at really low densities and stuff. But they knew, some of them were a little different than others, and they would start to burn them, and they would be able to see these different colors, which is kind of interesting. They're very reactive, so you never typically in nature are going to just find them all by themselves as like an actual lithium metal or sodium metal. You're only going to find them combined with other things. And they tend to form water-soluble compounds that are crystallized from seawater, then molten electrolyzed. So this is how we actually get them, okay, is we extract them from seawater, and then we melt them down, and then we can purify them down into these metals. Sometimes we do mine some of them and stuff. Like right now, we've been mining in South America for lithium, which is ethically ambiguous at best, and taking like salts that we get out of mines and then doing this whole electrolyzed process to them. And when they react with water, they tend to form basic solutions, and that's where this idea of alkaline comes from. Maybe you've heard of like alkaline water and stuff like that. It's basic water, and being basic is the opposite to acidic. And here's an example where you take sodium, you add it to water, and you form sodium hydroxide, which is like lye. If you've ever like made soap or something like that, you'd be familiar with this. And that process tends to release a lot of heat, so it's typically looks kind of almost explosive. If you put sodium into water, it's going to kind of explode with a lot of heat. In group 2, we have the alkali earth metals. They're harder, higher melting, and denser than the alkali metals. In magnesium, for instance, is actually used as a structural material, like magnesium alloy. You might have seen, like, I've seen bicycles and stuff made out of it because it's very light. They have their own unique flame tests again. So when they were trying to differentiate them, they were burning them and looking at the colors of the flame. They're reactive, but less so than the alkali metals. They tend to form stable, insoluble oxides, and that's how we usually will find them. So like calcium oxide is like lime. Magnesium oxide is pretty common. So these would be something that we would mine as opposed to like extracting from seawater. Their oxides are basic, right? So that's where it comes up with the alkaline earth. So they're coming out of the earth, but they're basic. And they tend to react with water when they're pure to form H2O or hydrogen gas. So moving to the other side of the periodic table, we have the halogens, and these are in group 17. They are nonmetals. Fluorine and chlorine are gases. Bromine is a liquid at room temperature, but only just barely. And iodine is a solid. You may be familiar with iodine from like the iodine that we use to like clean cuts and stuff like that. That's actually a solution of iodine. So that's solid iodine inside of water. They're all diatomic, which is something that we'll talk about later, but they tend to bind to themselves to make these molecules. They're very reactive. And that's why we use them for a lot of different stuff. Like we add chlorine and bromine to water to clean pools and stuff like that. Iodine's a cleaner. So we tend to not even see them in their own form, although that happens sometimes. A lot of times they are combined with something else. The chlorine and the bromine tend to react slowly with water to form these acids. And they tend to form with metals to make ionic compounds. So one of the big classics would be a metal like sodium reacts with chlorine to make sodium chloride, which is our table salt. And they all form these acids that we talked about when we were talking about with hydrogen. And as we go down the table, we tend to get stronger and stronger acids, which the strength of an acid isn't really something we're going to cover in this class, but there is like a trend that we would follow down with the periodic table. So our last group we'll talk about are the noble gases. These are group 18, so to the far right of the table. They're called the noble gases because they are all gases, and they all remain gases at most temperatures, actually. It's very difficult to get them to liquefy. They're very unreactive and practically inert, so that's the noble part of this. So they saw that as being a noble thing back in the day. They won't react with anything else. And we use that fact quite a bit, actually. We're familiar with helium from like balloons and stuff. It's lighter than air, so it'll make things float. We actually do liquefy helium in order to get something that's very, very cold. It's important cryogen, and that's like really central to technologies like the MRI, where we have to supercool a magnet and stuff like that. A lot of chemical analysis and stuff relies on helium, so it's actually kind of silly these days to put it in a balloon. The neon, we're familiar with this from like science, and it being unreactive is actually part of that. It's very hard to get it to remove or give an electron to. So when we put electricity through it, it won't even give off any electrons or anything like that. It would actually rather disperse that energy in the form of light than to move any of its own electrons. Argon, you may be familiar with if you've ever done like any kind of welding or anything like that. It's often used as like an inert gas in MIG and TIG welding to help prevent oxidation.